Alright, we'll start with the tree data structure. So what is in the menu today? We'll learn about types, traversals, and applications of a tree. So what is a tree? It is a data structure which is actually linked list under the hood, where there is one parent node and several or no child nodes. It basically resembles an actual tree in upside down form, and it's a hierarchical structure. So some of the jargons that you will hear around the tree data structure are node. So what is a node? This is basically the building block. It contains some data and references to its children nodes. Root. It is the topmost node, and you will always be given the address or reference to this node, which you can use to navigate around the tree. Depth of a node. It's nothing but the longest path from the root to any leaf node. But if you want the depth of a particular node, it's just the path from the root to that node. Siblings. Two nodes are said to be siblings if they have the same parent and are in the same level. And they are cousins if their parents do not match and they are in the same level. Types of trees. So we have some of the trees like, binary trees, binary search trees, AVL trees, red-black trees, n-array trees, segment trees, B or B plus trees, and ternary trees. But these are not all. There are much more types of trees. But don't panic, you don't need to learn all of them. Just focus on binary trees and binary search trees. A binary tree is a tree in which each node has at max 2 children and is typically referred to as the left child and right child. Binary search tree. It's a special type of binary tree where the left child of the node contains values less than the node and the right child contains values greater than the node. So this property makes searching in a BST efficient, and this property should be applied for every node in that tree. Now, applications of this property and why this binary search tree is designed this way, we'll see in future videos. Just know that this is how it is. AVL trees. So AVL trees are just binary search tree, but they are self-balancing. So the difference between the height of the left and the right subtree for any node cannot be more than 1. So as you can see from the image, that is an AVL tree, but let's say the last node is 4, right? If you had one more left child or right child, then 5 and 11 will not be balanced, right? So why are we self-balancing? Let's say you take a binary search tree and you enter all the nodes in ascending order. So one's right child will be 2, 2's right child will be 3, and let's say you have a tree, it'll be a skewed tree, it'll have only one length, and it's as good as a linked list or an array, right? So we don't get the benefits of having a tree which is skewed. So we have things like AVL trees which are self-balancing, and of course there are different criteria on how it gets self-balanced, and that's to go more deeper into it. So let's just put the brakes on that. So just know that AVL trees are binary search trees which are self-balancing. Red-black trees, they are also self-balancing binary search trees, but they use colors to keep them balanced. So again, how these colors are assigned to each node, how whole thing works has different criteria. They are quite elaborate. So just know that they use red and black colors to just make sure the whole tree is balanced. Ternary trees, just as what they sound, they are tree with at most 3 children nodes. N-array trees, tree with at most n number of children nodes. B or B plus trees, honestly, no one ever asks about these, but it's just another self-balancing tree, and it's just like AVL trees or red-black trees, but it's assumed that everything is in the main memory. So again, from interview standpoint, you don't need to learn about this, and that goes same for the next one, that is segment trees. It is used to store information about intervals. So still now the nodes contain values. Now we have segments. So it allows querying which of the stored segments contain a given point. So now we'll come to traversals. So we have 2 main traversals. One is breadth first search and depth first search. Breadth first search involves visiting all the nodes level by level, and we explore the nodes in the current level and then move on to the next one. So in the given tree, you can see that the first level, the root is always the first level. It contains the value 12. And then in the second level, we have 7 and 18. And in the third level, we have 5, 11, and 19. Next is the depth first search. In this, we try to cover the depth as much as possible before backtracking. So from 12, you try to go to 5, and then you go back to 7 and go back to 11. So that going from 5 to 7 is what they're calling as backtracking here. So in this we have three types. One is in order, pre-order, and post-order. In order, we first visit the left node, the root, and then the right node. Pre-order. What's pre-order? We visit the root and then we visit the left and right node. Post-order, we visit the left node, right node, and then the root. Now, don't panic. I'll go into the depths of how these calls in recursion work. And if you have trouble remembering the order, just remember the pre, in, and post prefixes that we have in the names of these traversals corresponds to the position of the root. The order is always from left and right? So in order, root comes in between. So left, root, right. In pre-order, root comes first, right? Pre. So root, left, right. In post order, it's the opposite. So left, right, and then root. Now, applications of the tree. So there are a lot of applications of trees. Three main ones are file systems. So normally any hierarchical storage, file system storage will use a tree data structure in the background. Family tree ancestry, this is very common. A lot of jargons that we talked about earlier even used words like cousins, siblings. We'll find questions like common ancestor, things like that. So it's basically a direct use case of trees. So family tree, ancestry. Decision trees in ML. So in ML we have this, we have to make sequential decisions, classification, regression tasks. All of these basically use tree data structure under the hood. And that's it. So that's it for this video. Thank you for watching. More videos will be coming in the future, which goes in depth into this tree data structure. And I really hope this video gave some insights to you. That's it. Thank you.